Okay, coming back to where we were last time, right? So we were looking at induction motor in the last lecture, right? All of you have already learned induction motor, you know the equivalent circuit, you know everything about induction motor. In fact, so to say, in the first course we have even talked about V by F control, we have seen little bit what is V by F control, why do you need it and all those things, right? Today's lecture we will revise that a little bit and then we would see how to do that actually using an inverter, right? So that's the objective of today's lecture. So inverter we saw gets used in multiple applications. One of them is an induction motor drive and very popular one, induction motor drive. If you see predominantly, right, there is conventionally after sort of let's say industrialization and so on, predominantly the load was some form of mechanical load, right? You want to either push something, you want to either roll something, you want to either lift something, you want to take the water out, you want yourself to go up in the lift or the escalator, or AC has a compressor again which is a rotating unit, right? So if you see in really around you, most of the loads, at least 15-20 years back, all the loads were some form of mechanical energy, right? They required some mechanical energy somewhere. And that's the reason these motors were like hugely popular and they are still popular, right? Because they are the one which converts electrical energy into mechanical. Storing an electrical energy, transmitting an electrical energy is much simpler than storing and transmitting probably a mechanical energy, right? It's much more efficient at the point of use, there is no pollution and so on. So it was a good source of energy, intermediate energy, but the load was always mechanical. So therefore motors made most sense. Do you know now why I say that 20 years back? Now what do you think, or rather in future what do you think would be the predominant load? Would it be again mechanical loads where motor in one way or the other, right? It could be different name of motor, it could be linear motor, actuator, whatever you want to call it, but some form of mechanical load, right? But in future what do you think? Would it be mechanical loads? Can anyone think of something? What would be the loads around you, let's say 20 years in future? I mean, of course, all of us can project, it may happen, it may not happen, we don't know. So after 20 years, what do you think would be the predominant loads? Would it be mechanical loads? Motors? ऐसा तो ही ना है कि वो था अभी वही रहेगा. Not necessarily like that, right? If that would have been the case, I would not even ask you this question. So yeah, still motors would remain, there is no question about it, but there will be one more type of load which will become predominant, which is data centers. Yeah, that's correct. Yeah. So now what is happening is all these AI applications that you use, right, they require tremendous amount of processing, and therefore there are like these huge data centers which require enormous amount of power for them to operate. Right. So that is going to be a big demand in future. Of course, if people are projecting this, all this AI, ML, everything would scale up, right? They would become smarter and smarter and the use case would increase, number of people using would increase. So you require a lot of processing, you require huge data centers, those data centers would require enormous power, right? And that would be contributing to a significant chunk of power requirement, and then those are not motors, right? Those are not mechanical requirement, those are basically electronics requirement. So you would still require some power electronics in converting it to the suitable voltage and the current, but not motors in that case. In fact, lot of these big companies who are heavily invested in AI and ML, they are also investing in power supplies required for those data centers, right? Because it's very difficult to process and power those chips which are, let's say, very small but require tremendous amount of current, right? But let's come back to today. So today we have predominantly motor load. So what we'll do in today's class is induction motor load. Maybe 20 years later, if I teach this course, we'll talk about some other load. But for today, we talk about induction motor. Quick revision of induction motor. The equivalent circuit of the induction motor was something like this. where this was XTH, this was RTH. XTH and RTH are the, what are XTH and RTH? Thevenin equivalent of the stator circuit, right, which had a parallel branch and a series branch, and then you have X2 prime, which is the rotor inductance or rather refer to the stator side, right, therefore there is a prime there, and then you have this R2 prime by S. This R2 prime by S term you can represent it as R2 prime plus R2 prime into S by 1 upon S. This is the part which represents, so whatever losses are happening here are actually not losses, are energy getting converted from electrical to mechanical, and whatever losses are happening here is actually the loss. Right, so far everything is okay, any doubt? Let me just erase this. It is the power going in R2 prime into S upon 1 minus S. 3 times dph square upon, this is basically I square dph plus x2 prime square plus dph plus R2 prime x square into 1 upon, right. This was the expression, you don't necessarily have to again remember it. This is nothing but I square term, and if you don't remember it, you can probably be able to do it correctly, because this is I square term, this is I square into R terms, right, and then this is R2 prime into 1 minus S by S, but here you have T mechanical into actual speed, which if you write in terms of synchronous speed, then those terms get cancelled, it comes there. There is something else I am missing, and that is an S here. Yeah. Is that okay? Somebody who remembers this formula, is this correct? Okay. And then we saw that this formula you can plot, right. This is gives you the mechanical torque with the slip S, where slip is nothing but synchronous speed minus the actual speed divided by the synchronous speed. So you can plot torque, you can call it tau or T mechanical, whatever. Okay, so far so good. When you did this machines lab, right, last semester, was the torque speed plotted this way or the other way around? Like you can just plot the speed on y-axis and torque on x-axis, right? You would see some books doing that also, but then yeah, don't get confused. Huh? As a student, I always used to get confused because different professor would come and then change the axis, and I'm like, ये तो कभी देखा नहीं है life में. If you plot it the other way around, right, looks very weird, you have never seen it before. So I generally try to plot always torque on y and speed on x axis, irrespective of whether it's a DC motor or a induction motor, but yeah, sometimes axis may change, but this one you remember, right. So this is a plot, you get this torque and this speed, right, you can operate anywhere. This is for a given value of voltage and frequency, right. All the other parameters are anyways constant, XTH, RTH, these are like constants, right, for that motor. So if you give it a certain voltage and frequency, then you get this plot. What is the meaning of this plot? The meaning of this plot is, why would? XTH will not be exactly constant, XTH will be constant, VTH will change. Yeah, that is okay. So XTH may not be constant, the inductance may be constant, that is fine. For a given voltage and frequency, you can operate anywhere. Of course, if you change the voltage and frequency, then this graph will change, and which we will plot subsequently. But for a given voltage and frequency, I agree, if you change the frequency, X will change, but not the L. Assume this is your load. What kind of load this looks like to be? What could this be? Can this be fan? This is because it appears that torque is proportional to square or maybe cube of speed, right? So it could be fan type of load or pump type of load. Let's say it's a fan. Now this is what we call it as a line start motor. What is the meaning of line start motor? Line start motor means you have taken this induction motor and you have just plugged it into a 3-phase line, right? That's what we call it as a line start motor. So if I say this is a line start means directly you have 3-phase AC 50 hertz 230 volt per phase, so 400 volt line to line, 400 volt 50 hertz you have directly connected it to the induction motor, right. There is nothing in between and you have just closed the switch, all the 3 phases together, and now what happens? That is what we call it as a line start. So if you see line start, if you are supplying with a fixed voltage and frequency, what would be the final point of operation? What would be the final settling speed of this machine? It would be this one, let me call it omega 1, right. Omega 1 would be the final speed at which this particular fan will rotate. The problem is that if you don't like your fan to be rotating such fast, right, you want to reduce it for convenience, right, or you want to speed it even more, then in line start, in this particular case where there is nothing between the line and the motor, there is no option, right, it would always operate at that speed. If you like to operate at this speed, you cannot do anything, it would automatically go there. The only thing probably you can do is if you have some way of tilting the blades of the fan, hypothetically, right, then you can tilt the blade of the fan and then this characteristics might change, right, and then the speed would change little bit, but moreover the air that is coming to you would change, so you can sort of still get some way of controlling the wind that is flowing to you, right, but you all understand that's going to be a much difficult task to do, right. So for a regular fan there is no way option, but you would operate at omega 1. So in this case you have a fixed speed. Is that okay? You can insert some resistance and try to do some things, but that would again be very lossy, right? You would have a lot of I square R losses. So if you don't do any resistance insertion, then it's more or less a fixed speed, you would not prefer to have it. The other thing is, or rather the other problem with this approach is that initially the speed is 0, right? So once you turn on this system, you just close the circuit breaker, speed is 0, so the load torque is this much, the mechanical torque is, or rather the torque produced is this much, right? And then the difference of the two torque would actually be used to accelerate your fan, right? Because the applied torque minus the load torque, tau is equal to, tau equals to what? Tau equals to what? Tau equals to m d torque is equals to m into d theta square by dt, right? D omega by dt, yeah, of course. So d omega by dt, or rather the acceleration, would depend on the difference of the torque, right? In this case it looks okay. If I would have drawn the torque speed characteristics to be like this, right, you can see this gap would be even smaller. If it's fan, it would accelerate, it would, I don't know what is happening, it would accelerate, it would what? Accelerate, it would accelerate, okay, anyways. I don't want to pronounce that word now. So there is a difference, the speed will increase, right, and as speed increases you are moving this side, as you are moving this side you see that the difference in the torque is higher, so further speed keeps on increasing till this point happens. At this instant both the torques are equal, right, so the d omega by dt will become equal to 0, so omega will become constant, right. I would pronounce it after half an hour, I think I will be able to pronounce it. If I try to do it now, it will be disaster. So you would settle here. This is a stable point of operation, all of you understand, right. So this is an unstable region, this is stable region. So it would just continue to operate here. If this is the characteristic, it will continue to operate here. But the initial torque, right, initial torque that gets applied is not much. You could have, or rather there is a possibility that you can even apply much higher torque even at the beginning, right. This graph does not really reflect that, but if I, for example, if I would have started this point little bit below, I would have started from here, gone up, come down, then you see that the initial torque is much lower than the maximum torque, right. So torque, let us say initial or starting, the starting torque is usually smaller than the maximum torque, right. That means you could have really used much more torque in the beginning, you could have achieved the desired speed much faster, right, then what you are doing it now. So this is the second limitation. If you do line start, that starting torque is much smaller than the maximum torque which the motor can apply to the load. Again, in fan case you may not really find it very useful, right. Oh, but it anyway starts in, maybe fraction 1 second, 2 seconds, it will anyways give you full speed, so you don't really mind. But now you think of this as a lift case, right. Yeah, you would like the initial acceleration to be fast maybe, or if you think of it as locomotive trains, right, heavily loaded, you would be happy using a little bit of extra torque in the beginning to pull it up, right, even if it's like heavily loaded train. So the initial torque does matter in lot of use cases, not in fans so much, but lot of other use cases. So this is also apparently one of the limitations. The third limitation is, what is the third limitation? What is the third limitation of a line start or directly line connected induction motor?
That induction motor gives consists of the torque required to start it is more than if the torque characteristics of a load, so at d=0, when above the torque characteristics of the motor, then you will never start.
Yeah, that is true. If you are, yeah, so what he is saying is, if you had your torque characteristics like this of the load, this motor would have never started, right. But there is a stable point of operation here, but you could have never reached this point, right. You would have just stuck here because the torque is negative, the motor would never be able to really overcome the initial torque itself, and that is true. So that I am just clubbing it with the second point, because if you would have had a higher starting torque, you could have avoided this situation, right. So this point I am sort of clubbing it with the starting torque is less than the maximum torque, right? It covers this point. Any other point? High initial current, right? And that you can see from this expression here right away, or you can just see from the equivalent circuit itself. Initially, if the speed is 0, right, that means value of slip is equals to 1. This is the rotor winding resistance, right, very, very small. So now if you apply full 230 volt per phase, the current that flows is significantly large, right, because the beginning at speed is 0, slip is equals to 1. Of course, when the speed picks up, then the slip value becomes very small. What is the usual slip value when the induction motor is running? Somewhere here, you have done experiments, so 3%, 5%. What do you mean by 5%? S is equals to 0.05, right? So 1 upon S is 20. Yeah, so this is 20 times, right? So you can imagine the current in that condition would be not exactly 20 times less, but roughly of the order you got an idea, right? So the initial current therefore could be, rule of thumb could be 5 to 10 times, 5 to 7 times higher. So high starting current, right? These are predominantly the 3 problems. Although the last and the second last does appear to be little bit counterintuitive. Torque is produced because of current. We are saying initially there is like 10 times the current, but we are saying initially the torque is not much. So if you just look at it very superficially, it would appear to be counterintuitive, but it is not, right? You understand. The current is high, but the starting torque is low, but the starting current is high, right? Any doubts so far? Otherwise we move to, yeah, it should not be less, right? I want it to be less. Why would I want my EV to the same word, not so much, right? So what I mean is that you would want the starting torque to be really high, right? Of course, for your application you would want that. It's your choice that you want to use it or not. That's a different thing. But here you have a limitation on the starting torque. Yeah, but reference is only as good as if the motor is capable of producing that torque, or the motor plus the control is capable of doing that. You can give me reference, you have to run 10 kilometers in X time, but if I am not running that fast, you cannot do much about it. You can just keep telling me that. So the reference will only tell me that, okay, run fast, but if I am not capable, I am not capable, right? Okay. So then we go for what is called as a as I am moving this curve, V by F is constant and either voltage or frequency is increasing. Both of them are increasing. Can you see what I have written here on the top? Dig raha hai? So this is the, let's say, the base case. Yes. Okay, anyone, all of you heard what he said? He's saying old fans, right, they would not start, but then if you use a stick and if you rotate it a little bit, then it starts. So what is the reason for that? Who wants to answer it? Raise your hand. I think I have asked you this question, or we have discussed somewhere, either in the lab or in the course. Who wants to answer it? Raise your hand. Go ahead. So So what she's saying is maybe over a period of time. That is a good question. She's saying that over a period of time, the load characteristics change from this one to this one, and therefore it becomes difficult to start. Is that what? No, you are not saying that. 4 or 5 what? It has 3 fins, 4 or 5 speed settings. You give it a full speed. So those speed settings are only changing the RMS voltage that gets applied. So you make it 5, still it won't move unless you hit it with a stick. It doesn't start at 5. Even if it would not start at 5 also, you have to use a stick to do that. Anyone else? Correct. But if that happens, have you seen that happening at your home? Okay. Next guy, have you seen that happening? Okay. Then what do? You cannot always use a stick to start your fan, right? So what do? Okay. So he's saying change the bearings. Let's see the next guy. What do you do if this happens? What do you do if this happens? But you cannot keep on doing every time. Na? It looks so odd if you have guests in your house and like pankha nahi chal raha hai, nuko abhi chalata hu. So once is fine, but you cannot keep doing. My question is, if it doesn't work, what do you do? If it doesn't work, ek do baar you use a stick, you turn it on. But what do you do then? Yeah, I mean you cannot keep doing it forever, na? Okay, closer. Next person. He's saying andar kuch conductor change karte hai, but go ahead. Anyone? Abhi nahi yaar. This is the third course, huh? We are teaching the same thing for the third time. Capacitor, yeah. Okay. So we change the capacitor. I think that's what you meant. And then it recovers, right? It becomes as good as new. How does changing the capacitor helps? Next person. Aage teri bari. Next person. You want to take a try? Just try. Try. Haan, good. Okay. Okay. Good. Yeah. Excellent. Yeah. This is correct answer. Huh? I think this sort of sums up everything. So the problem is initially your motor characteristics is like this, your fan is like this, right? So both are happy. You started even at lower speed. This point may be less, right? If you apply lesser voltage, na, how this characteristics changes the motor characteristics. If this is, let's say, motor 1, then the motor 2 will be like this, the motor 3 will be like this. Motor 3 means it's the same motor, but if you reduce the voltage, right? So if you want to start your fan even at speed 1, it does start, right? But over a period of time at speed 1, because speed 1 means the least amount of voltage you are applying to the fan, this point keeps on shifting downwards over a period of time. Why? Because this is not a 3-phase induction motor, this is a single phase induction motor. So the orthogonal component of the current is produced because of the capacitor, because capacitor would provide a 90-degree phase shift, and that is used to run the other winding, and therefore you get the torque. So over a period of time the capacitor becomes weaker, the orthogonal component becomes weaker, the starting torque becomes even lesser, right? And this guy would actually move down below this starting point of the fan itself, and therefore you will not be able to start at 1 or 2, it just starts at 3 or 4. But eventually it doesn't even start at 3 or 4 also, right? Then you just change the capacitor, put a new capacitor, it again works fine. This is the last time I am telling you, because I probably won't teach anything to you guys after this course, but make sure that now you remember it. Any doubt? That I think, there are two things. Now if you see your speed regulators, right? Do you have the speed regulator which is covers 2 switches kind of form factor? So there are speed regulators which occupy space equivalent to 1 switch. There are speed regulators which occupy space equivalent to 2 switches. Do you have the space regulator which occupies space equivalent to 2 switches? So the regulator which occupies space of 1 switch versus 2 switch has a completely different technology. The one which occupies 2 switch, if you open the regulator and if you just open it and you see inside, what do you see is capacitors inside the regulator also, and those capacitors acts as a voltage divider. So even those capacitors also degrade, and therefore you change the fan regulator capacitor, but you didn't change the regulator one. If you buy a new regulator, it will again work fine. Okay, now coming back, this is okay. Let's go to what we were doing. So yeah, single phase you would have that problem. 3-phase, over the time the torque will not reduce, right? If it's a 3-phase motor. In single phase motor that would happen. Okay, coming back. So this is the torque versus speed characteristics for a given V and F, and as you reduce voltage and frequency, maintaining the ratio constant, this is how the characteristics move. The maximum torque remains the same. We have, if you remember, we have derived the expression for maximum torque, and at that point we did see that even if you are reducing V and F by keeping V by F constant, your maximum torque is almost the same. Only thing is this position is shifting, right? So this you can think of it as an envelope of maximum torque, which is almost a horizontal line. Is that okay? So far it's fine. And then you have a load characteristics. I asked you to derive. Either way, either I would have asked you to derive or I would have derived. Most likely I would have asked you to derive, because that would require you to differentiate this expression, do d tau by d omega, put it equal to 0, solve something, and most likely I would have asked you to derive. Not in 240, but in 114, sorry, yeah. You derived, right? Who said we derived? Yeah. Okay, this is your load characteristics. Yeah, if you have not derived, you can go and derive now. Just differentiate it, make it equal to 0. And find the maximum torque, find the slip at which you are getting the maximum torque. Okay, now if you see in this case, now you can overcome all the 3 problems from there, right? One is fixed speed. Now you need not set your voltage and frequency corresponding to this one, which is, let's say, V1 F1. You can set it to V2 F2, right? And you can get at this speed. If you want to operate at this speed, you set it your V by F to P3 F3, and you will get exactly this speed. So you decide what speed you want to operate. You can operate at exactly the same speed, right? It's not a discrete steps. You can change the voltage and frequency, whatever you like, and therefore you can operate at whatever frequency you want to operate at. So the first problem is solved, which is fixed speed. The second problem is starting torque much less than the maximum torque. In this case, in the beginning, you can have your voltage as V4, F4, and you can get a really high electrical torque, and the mechanical torque remains the same, but you can get a very, very high starting torque as much as possible. Of course, the capability of the motor still limits the maximum torque, but with the motor capability, you get as maximum torque as possible. Is that okay? So in the beginning, you can keep your setting V4, F4 so that you get the maximum torque. As you make progress, you can change the setting and you can go to, slowly you can move to V2, F2 or V3, F3 or V1, F1 depending on what speed you eventually want to operate at. So the second problem also gets solved if you do V by F. Is that okay? Okay. The third problem was that of a high starting current. That also gets solved if you do V by F. In the beginning you would keep a very low voltage and very low frequency, and slowly you would increase the voltage and frequency. And now if you see the equivalent circuit, earlier the problem was this R2 prime by S was equal to R2 prime in the starting, right? And since R2 prime value was small, if you apply a large voltage, there will be a large current. But now you are applying a very small voltage in the beginning, right? So therefore the large current problem also doesn't occur. So therefore it doesn't even cause high starting current. So in a way all the 3 problems which were there get solved if you have a source of variable voltage, variable frequency, and you start your induction motor with that. Is that okay? The first part? Oh, you choose the voltage and frequency. So if you choose V3, F3, the intersection point will be here. Yeah, you choose the voltage and the frequency, and that would decide the point of operation. So you have a flexibility of choosing the point of operation. Any doubt? Any questions so far? Okay. Then the next question is that how do you actually operate it? There's a little bit more to this. Okay, before we do that, there's a little bit more. So similar to the DC machine, right? Now this is the point, this is the characteristics when you are applying the rated voltage and let's say 50 hertz frequency, right? Rated voltage and 50 hertz frequency, and a motor is rotating. Now can you operate the same motor in this region? Can you operate the motor at speed more than the base speed? Right? This corresponds to base speed. Can you operate the motor at speeds higher than the base speed? DC motor we were able to operate by doing field weakening. Here what you do is after this you cannot increase the voltage, but you can still increase the frequency, right? You can go from 50 to 55, 55 to 60, 60 to 65, but the voltage is now limited to V1, and therefore the new set of characteristics after this looks something like this. So your peak torque does reduce, but you can go further ahead in the speed, right? And if you see the envelope of this new thing, the overall envelope looks like this. So this is your constant torque zone, this is your constant torque zone up to this part, and beyond this is field or rather constant power zone, right? So you can even go at much higher speed. Of course your torque capability keeps on reducing, right? Here as you are moving, your voltage is fixed to the rated value and your frequency we are increasing as we are moving from left to right. So now if this was the characteristics, the original one, the speed you can operate maximum up to this speed. You can operate maximum up to this speed, right? You can operate maximum up to this speed because this is the farthest intersection that you can find. You can set your voltage and frequency to be even higher, but since there is no intersection point between this curve and this curve, it would not operate at higher speed, right? So even if you are setting whatever 100 hertz, but doesn't matter, your rotor will not take you there. It will actually be a standstill position. It will not even move. So, but you can maximum go up to is this point. Of course, if you have a load which goes like this, you can practically go up to here. So you can go at a higher speed, of course, depending on the load requirement, but there is a way of going up to higher speed more than the base speed. Very similar to the DC machine, right? In fact, the curve looks very similar, the envelope looks very similar as what it was in DC machine, right? And now if you have noticed your experiment that you have done, right, you had that setting in the lab, you had this V by F drives, it had those settings and you can go up to 60 hertz in that, I think. You cannot go beyond 60 hertz. Till 50 hertz it would do V by F, and after 50 to 60 it would maintain the voltage and it would just increase the frequency. So you can get at least 1 or 2 more steps, maybe not too much, but few more steps. I wanted to bring the drive again, but I forgot to do that. But you all remember that how it looked like, right? The induction motor drive, the box which had this small display and few buttons to set up the frequency. Okay. Any questions so far? So now the question is, how does that induction motor drive which we have seen achieves this thing, right? How does it achieve it? By what I mean by that is, now the way we are talking about is, in the beginning you said this V by F and then you said this V by F based on your speed, but these are all sort of what do you say, we are not doing it every time when you are doing the experiment. You are not manually changing those settings every instant, right? You would program it once, then you would connect it to the machine would start, run, you would take the readings, then of course you would change the settings. but you are not changing the settings on the fly as, oh, motor start ho gaya, abhi change karo, V4 se V1 pe jao. You are not doing that way, right? So you would just put the setting. So what was those settings and what was actually going on in that drive? So in the setting you were setting, let's say V3 F3, right? Let's say V3 F3 was 45 Hertz, V3 was corresponding to 45 Hertz. So you were setting F3 on the display and you pressed enter. Now if that drive directly applies F3 to the motor, what will happen? You will have all the problems, right? Because F3 characteristics is this one. This is your load characteristics. You won't get the maximum torque, substantial voltage, you would get a large inrush current, all the problems would be there. So although on the drive, display you were setting 45 Hertz, but there is a processor inside which knew that, okay, you eventually want to run at 45 Hertz, but then it would do a soft start, right? It would initially apply a very low voltage and frequency, then it would slowly increase the voltage and frequency over a few seconds, estimating that the motor would also take few seconds to go from this speed to that speed. That drive didn't have any speed feedback. If you remember, there was no connection to the speed. It was only connected to the 3 terminals, right? And therefore, it didn't actually know what is the speed. So from some calculations, some estimations, it would initially apply a very low frequency and voltage. And now this guy knows that induction motor would have started. Then slowly this guy would increase voltage and frequency and take it up to the desired set point which you have set on the display. Now once you have reached the desired frequency, the speed would of course again depend on the load characteristics intersection, right. So this is how the drive which you were using in the experiment was working. Should I repeat anything? Any part? So this is what roughly was happening in the drive that we were using in the lab, right. You were setting a reference speed or a reference frequency f star. There is a processor, there is a microcontroller sitting inside that motor drive, which would, based on the command, which would generate an frequency, actual frequency command, right. That actual frequency command in the beginning would be much smaller and then slowly it would increase and eventually set to this f star. This, since V by f has to be maintained constant, once the frequency is there, you do V by f, look at a graph, it could be a lookup table or a multiplication, you get the voltage reference. Now this voltage and frequency has to be actually applied to the motor. How it was getting applied is there was an inverter inside that box, right. And now this voltage and frequency, if you see these two things combined, would give you the reference value for A phase voltage, VA star, which is nothing but you want, let's say V is the RMS, if V is the RMS, V into root 2 times cos of 2 pi Ft, right. You wanted to realize this voltage across the induction motor. So you have created the sine, you have used the sine triangle comparison, where the sinusoidal was m times cos of omega t, right. You have calculated m so that you get this voltage, then you use sine triangle comparison, you generate the PWM pulses, those PWM pulses goes to the actual inverter, there is a DC bus there, actual inverter creates the voltages which goes to the induction motor. So everything was happening in that drive, right. This is something which we learned few lectures before, right. The inverter and the sine triangle PWM which was also there, this controller is also there, and this logic of slowly increasing the frequency and voltage is also there. Does it sort of sum up, does it add up? to you everything that we have done over last few lectures, right? Sort of an example of what we have learned applied for induction motor drive. Sorry? What is V? VA is the A phase voltage. So, yeah, VA is the A phase voltage, which is V, if V is the magnitude, V into root 2 times cos of 2 pi f t. If B phase will be minus 120 degrees, C phase will be minus 240 degrees, right? Balanced 3 phase supplies. Any question? Any doubt? I knew you were differentiating it, na? Okay, we'll discuss it after the class. We'll discuss it after the class, don't worry. There are some approximations, so we'll talk it. It's not exactly constant, it changes slightly, so there are some approximations, we can talk it after the class. Any doubt? Any question about this implementation? Okay, if there are no questions, then you tell me what are the problems here. Of course, we have solved few problems, but it's still not the best solution, right? Still not the best solution. Why it's not the best solution? What it does is, yes, it gives you low starting current, right? Okay, before we do that quickly, how do you get this DC supply to the inverter? How do you get this DC source to the inverter? Because for inverter to produce AC voltages of your desirable voltage and frequency, which an inverter can do, it requires a DC source, right? So where does this DC source comes from in your drive that you had in experiment? Rectification, right? You had an AC supplier, you would plug it into a single phase AC supplier and you would have a full bridge rectifier, and that full bridge rectifier will rectify the AC supply and will give you a DC voltage, right? So this DC was actually getting produced by a single phase AC and going to most likely full bridge rectifier, and then you have a capacitor to make sure that ripples are not there. There's almost a smooth DC, and once you have this smooth DC of how much value, approximately 350 volt, which is the peak value of the AC voltage, this is something which you supply to the inverter, right? So this box had everything. This box had rectifier, this capacitor, this inverter, a controller, everything was there in this small form factor. What are the problems with this one? Yes, the initial current is low. Yes, you can get a high starting torque, but the first objective, which was you want to run it at the desired speed, is still not completely met. Why? Because you are setting frequency to be 50 hertz, let's say, or 45 hertz. Depending on the load, this is the point of intersection. If you turn on 2 more bulbs, and you remember the lab setup, right? You would turn on few more loads, your frequency, your speed will drop. The frequency is the same, but your actual speed will drop, right? Actual speed goes from point A to point B. If you turn on few more loads, it drops further. So actually your speed was not constant, right? Still changing with the load turning on and off, which is what you would not want, right? You would want your speed to be constant, correct? So inherently you can do it. How can you do it? If you are observing it, you can change the frequency. So for example, now you see you are operating at point A, right? Suddenly somebody turned on 2 more bulbs, you have moved to point B. Your speed has reduced. You know what to do. You have to increase the frequency a little bit more. If you increase the frequency a little bit more, you would go to this characteristics, the new one, right? And you would move to point C. Point C and point A, same speed, right? So if you have some mechanism of actually observing the speed, then you can always build a small logic, right? And write a small code in microcontroller to adjust the frequency so that you are always operating at the same speed. Is that okay? Should I repeat once again? This one here sets the reference frequency. So you give it frequency 45 hertz, 50 hertz, it sets it. Doesn't set the reference speed, sets the frequency, not the speed. Of course, if the frequency is set, then depending on the load, the speed will not vary much, right? It would be within this region, and this region, this is usually sharp, right? So your speed doesn't vary much if you are at a fixed frequency, but it still varies. If you really want to have a fixed speed operation, then you have to have a little bit more logic. What you can do is, if you are operating at A, load increase, you went to B because same frequency, you would go to point B. Now point B, you know the speed has reduced even though the frequency was same. So you can ask your microcontroller to increase the frequency a little bit so that you move to C so that you maintain the same speed. So if you want to really do a tight speed control, a very regulated speed, you have to have some mechanism of measuring the speed, and then you can adjust these references coming out of these blocks. Does it make sense? Is that okay? Is that basic logic okay? You want me to repeat again? Which part? Okay. Okay, look at point A, B and C. You can see it right from the back. Point A, B, C are visible. You have set a voltage and frequency on the console, right? It had its logic. The motor started slowly. The frequency initially was very low, and slowly the voltage and frequency has increased, and it has reached to the frequency at which you have set the controller at 50 hertz or 45 hertz, whatever you have set. And now this is the F3 that you have set. You are operating at F3 and your load is this characteristics. So your point of operation is A. At point of operation A, you have a certain speed which is, let's say, omega 1, right? Somebody changed the load characteristics. Load characteristics move from this guy to the white one. It moved upward. You increase the load, right? Now for the same source characteristics, because source is now settled, speed has settled, the frequency is the same, the intersection point has moved from this point to B point. But B point the speed is little less than A. B point the speed is, let's say, omega 2, right? Speed has reduced. Now if you have no clue of the actual speed, then nothing will happen. You will operate at omega 2. And to be very honest, omega 1 and omega 2 are not going to be very far apart also, right? They would be nearby, because slip would probably change from, let's say, 3% to 5% or 7%. So it's like 2-3% speed change, right? Maybe you mind, maybe you don't mind. But if you really want to have a very tight speed control, then you would want not to run at omega 2, but to again come at omega 1. If you want to come at omega 1, then your point of intersection has to be C. And for your point of intersection to be at C, your frequency and voltage has to be increased a little bit more, right? So if you have a way of measuring this speed, taking inside the microcontroller, then you can write a small logic in the microcontroller that, look boss, you always look at the actual speed. If the actual speed is less than what I want, then increase the frequency. Don't stick to my reference point of frequency, stick to my reference point of speed. So instead of giving frequency as the reference point, then you would give your speed as the reference point, right? And frequency this controller can generate for you. Is that okay? But this would require a speed to go, or a speed feedback to go inside the microcontroller, inside the speed controller. Yeah, depending on whether you are in the field weakening region or you are in the constant torque region. In constant torque, it would increase both. After that, it would maintain voltage and increase the frequency. Is that okay? Okay, so I will explain you one such block diagram which would give you little bit more detail of how you can use the speed. But you got the basic idea, the basic logic, but there is one implementation which I'll draw, but there are some questions, okay. Okay, so I'll come back and answer your questions. You're saying you have to increase the frequency, by how much should you increase, right? What is your question? How do you measure the speed? You can't use a tachometer, yeah, okay. So that's a question. Okay, let me answer yours first. So his question is, how do you actually measure the speed? So what is a tachometer? Tachometer could be, let's say, some form of a LED light or an IR light, and then some disc is rotating and it's just measuring or counting the number of pulses that light emits and the receiver receives over 1 seconds, right? And that's how you would get rotations per second, right? So this is anyways electronics signals. For our convenience, we put a display and then on that display it comes out 2000 RPM, right? But actually it's an electronic signal. So why can't you take that electronic signal and supply to a microcontroller which will have an analog to digital converter anyways, right? It would have GPIOs also. The counting mechanism also you can do in microcontroller if you want. Right? So measuring the speed using an electronic circuit is not that challenging. What was her question? How do you know how much to increase, right? This is basically a basic control systems kind of a problem. By now you have done control systems course, right? You have done some application in that course. Any specific use case did you consider? You have done PID control? No, class also you have done PI control. Okay, for what application you have done that control in the class? Oh, is it? Okay, so what was the input, what was the output to that control? No, let's. No, can you go a little slowly? What you were doing there, and how is it different from here? Because it's a different course. Yeah. Correct. Okay. Okay. So you know this is how eventually, right? Eventually, what is being broken down into different engineering domains or different courses. In real life, nothing is like broken down, right? It's all continuous. So what we are explaining here is more on the control logic part of the things for an application which is more related to power. If you look at it, in reality, if you have to implement it, you have to do a modeling of the induction motor, which by the way we have done. The one which we have done is more of a steady state model, but in reality, if you really are very, for you the transient response and all those things matters a lot, then you would do a transient model of the induction motor also. You would do the modeling of the inverter, this would be your plant, this would be your controller, so everything what you have learned there fits in here, and whatever you learn here fits there also, right? Why we are not doing exactly same thing is because two reasons. At this point here we are mostly looking at steady state speeds, right? We are not so much looking at the overshoots. But in reality everything matters. When you turn on these two more bulbs, right? Do you think you go from speed 1 to speed 2 and just settle there? No. There is going to be an overshoot or undershoot. But we are not getting into those things. But this is what probably you are learning more there. And you are learning how to tune the PI controller to do that, right? Which we are not doing it here. But there, like for the same thing, you have to apply both for actually to build a system and to operate a system. So now since all of you know what is a PI control, I would use that to draw the control diagram for this one, right? And let's see how much we can understand. This could be omega or it could be speed in RPM, which I am representing as N. Okay, first let's draw it, then I will explain you. I think that is it. We'll try to go through it, and if there's a mistake, we'll figure out. But first of all of you have to draw it. Okay, let's now sort of see what it is. So this is your actual speed feedback. This is you are measuring from the motor somehow using an electronic circuit, right? And some sensors, maybe IR sensors, maybe Hall sensors, some sort of sensor, you are measuring the speed. The speed could be in radians per second, of course it can be in RPM also, right? So it could be either N, which is in RPM, or it could be omega. You can figure out whichever implementation you want. In your this different drive, instead of setting the frequency, you are setting the reference speed, right? And this actual speed gets compared with the reference speed. Of course, in the beginning, the actual speed is 0, the reference speed is, you have set it to, let's say, 1000 RPM. So the error comes out to be positive. If error comes out to be positive, it goes to a PI controller, right? Assuming that in this system, we keep a very low value of P and a very reasonably good value of I. So this error would slowly start getting integrated or accumulated to give you this expression of, we call it as, let's say, delta F, right? So initially speed is 0, omega is 0, omega star is 1000 RPM, error is positive, your delta F is started rising from 0. Let's say it went from 0 to 0.1 hertz, 0.2 hertz, 0.3 hertz, 0.4 hertz. Initially your speed is 0, so your F, which comes from 120 F by P, N is equal to 120 F by P, is also 0. So this 0.1 hertz added to 0 gives you 0.1 hertz. You apply this 0.1 hertz to the motor, and depending on the corresponding to the 0.1 hertz, you find the voltage and you apply that voltage to the motor. So now you have applied this first characteristics. You have applied this first characteristics, right? This is the torque speed. You have applied the first characteristics, the motor starts rotating, right? Motor starts rotating. As the motor rotates, your speed has become a little bit more. Let's say it has gone from 0 to now 50 RPM. Now 50 minus 1000, still positive, still it would be integrating, still it would be adding a delta F to the frequency corresponding to the 50 hertz, which is existing frequency. So now your frequency goes further a little bit ahead. So now you move here, right? From here you started. As soon as you reached here, you change the frequency, then you again change the frequency, then you keep on doing it till your reference frequency is achieved. So you come here, and you can, as soon as this becomes equal to this, right, the error becomes 0, this remains constant after that, and this system settles to a steady state where this F, which is the actual frequency, plus this delta F, this is the frequency corresponding to rotation, plus delta F is your set frequency for the inverter, right. So let's say this is the point where this is the frequency corresponding to, which is the synchronous frequency, right, or the applied frequency, which is this one here, this is F applied, and the actual frequency is corresponding to this point, right, this is 120 F by P, omega is N is equal to 120 F by P. So one frequency, this output frequency is the frequency applied, right, which is the synchronous frequency. This is the actual speed or the frequency calculated based on the actual speed, right, based on the difference in the slip speed, which is this frequency. Okay, not okay. No, this frequency is different from this frequency. This frequency has a delta F and then the actual frequency. Which two? These two are same, of course. This is speed, right? This is the same speed written as frequency, 120 F by P. So these are actually the actual speed, N, omega, F. These are the actual speeds. This is the setting, the frequency setting, which earlier you were doing it yourself, now this controller is doing it for you. right? Is that PI controller? Sorry? Yeah, you can use something else, you can use PID, whatever control systems you have learned, some lag lead, compensator, whatever you have learned, you can apply anything you want. Oh, what it is doing, it's doing the job what we would have done, right? You would have seen the frequency speed, or speed is low, increase the frequency, this guy is doing the same job. Now, this guy can do that job much faster if you use PID, this guy can be very sluggish if you use only integrator. So, depending on the application you can choose, you can design the values and coefficients, right. But I am happy that you have done a parallel course where you have learned PI and PID, so I do not have to explain you that part. So, good. Any questions? Do you guys know what this symbol means? What this symbol means? In your control systems, have you seen this symbol before? No, this means saturation, right? So, what it means is your delta F will limit to some delta F max and some delta F min. In our case, delta F min could be 0 also, but there is a maximum delta F, right? So, this symbol usually means saturation on the output. Yeah, again, in the basic thing you would usually expect there is no saturation, but you need practically a saturation, and I will tell you why you need a saturation. Let me tell you why you require saturation. So, initially your speed was 0, right? Your reference was this one and you were accelerating, a little bit closer, I will get back to that. I don't know what happened, so sorry. Anyways, your speed is increasing. But then let us say your PI controller is relatively fast. So what will happen, your speed is increasing slowly, but this guy is like really excited. So what it will do is it will keep on increasing delta very fast. So even though you are somewhere here, but in that short time this guy can take the delta F to such a large value that your characteristics is this one, the last one. And if that is the case, you understand the inverse current will be large, your initial torque has come down, all sort of problems, right. So you don't want this guy to be really fast, you want actually this guy to be of the same order of response as that of the inertia of the motor, because the motor is a slow system, right, it takes its time to start and rotate. So therefore, to make it slow, one is of course you would choose the values of Kp and Ki appropriately to make it slow. The other thing is you put a limit on delta F max so that you are never really far away from the point of operation. You would always be just little bit ahead of the point of operation, right? And that how much ahead you can control by setting up this delta F max, right? So actually you have to go through it once again. If you have a doubt in this, we can discuss it again. This is one such implementation for speed control. This is not the implementation of the speed control. You can build your own logic. There are so many logics which are there. People have figured out how to make it faster, how to make it slower, how to make it even better, right? It's something which has been going on from at least decades of quite a few decades. So there are different logics which have been built. This is the most simplest one, so to say, and therefore this is something which we cover in this course. If eventually if you end up doing some advanced motor control courses, which are usually elective courses, you can learn a little bit more about other control as well, but not this course. This is maximum we do in this course. Any question here, any doubt here? Yeah. Yeah, main reason is to make sure that you are not really going ahead of the actual operating speed too much, because if you go ahead of too much, all the problems of high current, low starting torque, everything sort of comes back, right. So mainly it is to restrict you from not going too far ahead of where you are now, right. That's the main reason. Okay, this doubt is answered, so we will stop here.